A very fine morning, my dear students. Hope you all will be fine by the grace of God. Students, today we will continue with the same chapter, that is chapter number 4, Effect of Electric Current. Before starting today's session, let us recall what we have studied or what we have discussed in our previous lecture. In our previous lecture, we have discussed about magnetic effect of a current, right hand thumb rule, magnetic field produced by the current through a circular loop of conducting wire, magnetic field due to current in solenoid, force acting on current carrying conductor in the magnetic field, Fleming's left hand rule, etc. In today's session, we will study about electric motor, electromagnetic induction, Faraday's law of induction, Fleming's right hand rule, AC and DC current, electric generator, etc. So, children, here I will show you some slides that you see, and after that we will start our explanation. Here you can see the AC generator is there. The structure I'll explain you later. And one more generator is there. That is the DC generator. So both are there. Now let us start our explanation part. So children, we are starting from here, electric motor. So we will see today that it is a electric motor. It is a device which is changing electrical energy into mechanical energy, and it is called as electric motor. In our daily life, this motor is like a boon because it is used in the fans, refrigerator, mixer, washing machine, computer, electric pumps, so many things it is used. So this point you have to underline. That what is electric motor? This is very important point. So children, you can see here, this is electric motor. Let us learn how it works. Here is the structure. Children, here I will show you how it works. First of all, you understand the structure. Here, these are the North Pole and South Pole magnet. These air magnets are kept. We can use a horseshoe magnet also. Then this is the axle that we use. Here, I'll show with a different color. Here we can see this is the coil, copper wire that is having a resistive coating. That means current should not touch in our hand. It is avoiding that touch. See, this is AB coil. This one is AB coil, and this side it is CD coil. These both are joined here, and here carbon brushes are there. You can see these carbon brushes. I'll show you. Children, these are the carbon brushes. Here we can see. These are the carbon brushes. And this is the outer arrangement of the electric current. Wait, I'll show you. Here we can see these are the cells, this is the key, and this wire is there. So this is all about the structure. So it is electric motor principle and working. Now we will see the electric motor is consist of rectangular loop of the copper wire which is having residue coating. Residue coating mean from outside the coating should be there. So if we'll come by chance in touch of that, the shock will not get the shock. Then it is placed between the north pole and south pole of the magnet. The branches AB and CD are perpendicular to the direction of magnetic field. So that we have to keep in mind that their branch this should be in the perpendicular direction. The two ends of the loop are connected to the two halves X and Y of the split ring. So here you can see the split ring is there, children. This is the split ring, you can see here. This is the split ring. So it is they are connected to that, and the two halves of the ring, they are having the residue coating on their inner surface, as well as they are tightly fitted to the axle. Axle already I told, this is the axle. Now the two halves of the split ring X and Y, they have their outer conducting surface in contact with the two stationary carbon brushes that are E and F. Already I have shown you. I'll show you with the different color again. So here you can see these carbon brushes are there. Already I explained you. Now when the circuit is completed, then the current is flowing in the branch AB of the loop, and it is going from A to B. So wait, let me show you here. So it is going this way, in this direction. Now the direction of magnetic field is from north pole to south pole. So according to Fleming's left hand rule, a force is exerted on AB branch and it pushes down. So what will happen? The current in the CD branch will flow in the opposite direction to that in comparison of the AB branch, and therefore a force will be exerted on the branch CD in upward direction. So when this AB is going in the downward direction, then this one is just pushing up to the upward direction. The loop and the axle, they start rotating this way due to this force, downward and upward, AB in the downward and CD in the upward force. Due to that, it start rotating. So the loop and the axis start rotating in anti-clockwise, and after half rotation, the two halves of the split ring X and Y, they come in contact with the carbon brushes. So when they come in contact with the carbon brushes, the current in the loop start flowing in the direction of DCBA. So you can see this direction, DCBA, this direction. So now a force is exerted on the branch DC in downward direction and on the branch BA in upward direction. That means now it is reverse after half rotation. So what will happen? That the loop continues to rotate in anti-clockwise direction, and the current in the loop is reversed. Reverse means it become ulta, it become just opposite after each half rotation, and the loop and the axle continue to rotate in anti-clockwise direction. So mostly commercial motors run on this principle, but practical changes are made according to the construction and need. Now here one question is there, children. Here this is the question. This question, that why are the brushes, carbon brushes used? How do this work? So why the carbon brushes are used? Because these brushes are made of carbon, so they offer less resistance and they act as a good conductor, as well as they are cheapest to replace also. And why the brushes are there? The brushes make contact with the split ring and they are responsible for making the break and to make and break the circuit. That is why these brushes are used. Now next is electromagnetic conduction. So children, we will see now this electromagnetic conduction. In this we will see that if we will keep an electric conductor in a magnetic field in such direction of current flowing through the conductor in perpendicular to the magnetic field, that means in which direction the magnetic field is there, the current should flow perpendicular to that direction. Then a force is exerted on the conductor, and because of this the conductor moves. But if an electric current is moving in a magnetic field, or the magnetic field around a stationary conductor is changing, then what will happen? So in order to find out this all, a research was made by a scientist. His name was Michael Faraday. So this point you have to underline. That his name was, a research was made, and his in year 1831. Faraday showed that an electric current can be produced in a conductor with the help of moving magnet. Now, children, here, wait. This full is cancelled for you. This also. So, let us see this diagram now. This diagram we are going to see. In this diagram, a galvanometer is there. Now, what is galvanometer? That I'll let you know. Galvanometer is a sensitive device which works on the same principle as electric motor, and we can measure the current through it. Electrical measurement. It is used for electrical measurement. Now, with the help of galvanometer, we can detect small current, and same way the ammeter is there, that you will study further, that is used for measuring large current. This is the difference between ammeter and galvanometer. Now children, we have to collect this all materials. We can see here that this is galvanometer. Here the magnet there is there. These are the magnets. So we have to arrange this way, and this is experiment that if a conducting wire is kept moving in a magnetic field, a current is produced in it. So we have to complete the circuit by connecting the galvanometer. Then we will keep the bar magnet erect in such a way that its north or south pole is just below the copper wire. Now, if the wire is kept moving from A to B, here you can see children, I'll show you which. You can see here that this is the A position of wire here. Then now we'll see here the B position with the different color I am showing. So the wire is moving from A to B. The pointer of the galvanometer get deflected. Deflected means it changed the place. This is called the Faraday's electromagnetic induction. Now if we'll move the magnet with the wire fixed, the galvanometer pointer will get deflected. So this point you have to underline. That this is called the Faraday's electromagnetic induction. Now come to the next point here. We will see when the current in the solenoid coil is switched on or off. This is the diagram. Here we can see this is galvanometer is kept here. This is galvanometer here, and this is solenoid coil. This is key, and here the battery is there. Let us see now. In this diagram, we will see here in this experiment, if we will open the plug key and make the current 0 in the coil, So key I have shown you here, again I'll show you. This is the key, children. So this way one pointer is there, that if this way, so if we'll put this in key, then current start flowing, and if we'll remove, then current stops. So here is the battery, and this is galvanometer, this is coil, this is solenoid coil. So we'll see the deflection in the galvanometer. Now children, uh, the pointer of the galvanometer deflects to a side and quickly comes back to zero. But if the current in the coil is started again, the pointer again deflects to the other side and return back to the zero. So when the electrical current is flowing through the solenoid coil and the solenoid coil is displayed with respect to the coil, the current is still produced in the coil. That means we are changing. Suppose this solenoid coil is displaced to this side, then also the current is flowing. Now let us see the next figure, that when a current, wait, I'll show you. This was that when a current is passing through the solenoid coil and the coil is displaced laterally with respect to the coil. So here the coil is displaced laterally. Let us see now the next one. Here this arrangement, here we can see this is the coil, this is solenoid coil, this is key, and this is battery, this is galvanometer, and already I told that this way small plug is there, that is put in the key. Here it is put here. So now we will see that this figure is showing us that when a current passing through the solenoid coil and the solenoid coil is displaced longitudinally with respect to the coil. In first case it was displaced laterally, in this case it is displaced longitudinally. Now if the solenoid coil is kept stationary, a change in the current in the solenoid coil produces a current in the coil. But if the solenoid coil is moved towards or away from the coil, we can see the deflection in the galvanometer. As well as the faster is the displacement of solenoid, larger will be the deflection in the galvanometer pointer. So you all know that in galvanometer one pointer is there, so that is pointing the current. A current is produced in the coil, or if the solenoid coil is moved toward the coil, then also the current is produced in the coil. So we had to see that this point, we had to, this galvanometer, this point you have to underline, this point, this is important point. Now children, we'll see the Faraday's law of induction. This point we are going to see. Let us see the show you diagram, children. This is the diagram. Here we can see this is showing the direction of the magnetic field, this is showing motion of a conductor, and this is showing the direction of the induced current. So here a current which is switched on or off in the solenoid coil, and we can say a current is induced in the coil. Induced means which is artificially prepared. Here that something is forcefully made to flow the current. So such as induction is also observed in the current in the solenoid coil when it is increase or decrease. So current is induced in the coil when it moves aside from the solenoid, from front of a solenoid, or from these experiment what we conclude that the number of magnetic lines of force which are passing through the coil, if it is changed, then the current also will be more in the induced coil, more induction of the current will be there in the coil. This is known as the Faraday's law of induction, and the current which is produced, that is called the induced current. So this point you have to underline. This full you have to underline. Let us see now Fleming right hand rule. So far we have seen Fleming's left hand rule. This is the Fleming's right hand rule. See here children, this is showing the direction. So this is the direction of magnetic field, this is the direction of induced current, and this is the direction of conductor. This is Fleming right hand rule. These both rule are very important, left hand rule and right hand rule. So here we'll see that when the direction of motion of electric conductor is perpendicular to the magnetic field. So you can see here this is electric conductor and direction of magnetic field is just perpendicular to it. Then Fleming, in order to show the direction of induced current, Fleming right hand rule is very useful to us. So we can see here this is the direction of induced current, and we have to stretch the index finger and the middle finger in such a way that they will be perpendicular to each other. So in this, the thumb indicate the direction of motion of conductor, the index finger the direction of magnetic field, and middle finger shows the direction of induced current. This is known as the Fleming's right hand rule. It is very important children, you have to learn it by heart. So this point you have to underline. Where to see? This full you have to learn. Now children, this is cancelled for you. Here this full part is cancelled for you. Now this also cancel for you. Now children will see the electric generator. So here we will see that the experiment which are based on electromagnetic induction we have seen. Here the current which is produced in these experiments were having very small magnitude. That means very low. This was very low capability, low ability. Now we'll see here that means it was small current, small, it was of small magnitude, but the principle can be used or utilized for use of the mankind to produce large current also. So when the mechanical energy is used to rotate the current which is carrying the coil in a magnetic field around an axle, thereby it is producing what? Electricity. So we can see a copper wire in ABCD. It is kept between the two poles pieces of a magnet. The two ends of the coil are connected to the conducting ring R1 and R2. So I'll show you in the figure. Just see. Already I have shown you AC and DC. Here we can see that two are the magnetic field. These are magnet. Here North Pole, and this is North Pole, and this is South Pole. And this is the coil is kept here. Now this is the axle. This one we can see, this is the axle. You can see, and these are the, I'll show with different color. These are the rings we can see. Now these are conducting rings as R1 and R2, R1, and this is R2. Now here again carbon brushes are there. We can see these carbon brushes are there. As they are labeled as B1 and B2. So I'll show with different color. Carbon brushes here you can see B1 and B2. Now this is the external, the stationary carbon brushes are there, and that are connected to the galvanometer. Now children, we'll see it is showing the direction of the current in the circuit. When it is rotating, the branch AB goes up and the branch CD goes down. That means when this wire is rotating, which is used as a coil, then this change occurs. Now see children, this here we can see this is the galvanometer is put here, and this is the outer wire, how the electric current is flowing. Now, according to the Fleming's right hand rule, electric current is produced in the branches AB and CD. So, let us see here. Children, we'll see this is AB branch. And this is CD branch. So how the current is flowing? That it is flowing as ABCD. That means this way, ABCD. Now in the external circuit, the current flows from B2 to B1. That means this circuit, it goes from B2 to B1 this way. Now if instead of one loop coil, a coil which is consisting of the several turns is used, that means this is one loop only, na? What coil you can see here? This coil, that is one loop only. But instead of this, if many loops are used, then what will happen? That after half rotation, the branch AB takes the place of branch CD and the branch CD takes position of the branch AB, and therefore induced current will go as DCBA. So how it goes? DC, then BA. It goes this way. So children, here we'll see that the branch BA is always in contact with the branch B1, and that means this branch is always in contact with the B1, whilst this branch is always in contact with the B2. So this process repeats after every half rotation and alternating current is produced. This is what called the AC generator. So this point you have to underline. So this is all about the electric generator, and this way the current is produced. Now children, here we'll see this part is cancelled for you. Okay, so now here this chapter is completed. Again I am telling, whatever the important points are there, write down in your 100 pages book, learn it and practice this all diagram, learn all the rules, because these all rules, right hand rule, left hand rule, these all are very Fleming rule, Faraday's rule, these all are very important. Out of these, at least one rule you will get in board exam. So it is better to learn. I hope you might have understood what I taught. Read the lesson thoroughly, each and every sentence, and see. If still any doubt, you can ask me, children. You can text me and can ask me. Thank you, children. So what diagram you have to practice, that I'll let you know. Electric generator you have to practice. Fleming right hand rule, that you have to practice and learn the rule also. Then electric motor, principle and working, this is also very important topic, you can put important for that. Then electric motor, that is also important. So this all you have to learn from this chapter. Electric circuits, about fuses, magnetic effect of a current, these all are important things, children. And practice the numerical also. So thank you, children. I am ending my lecture here.